Okay, welcome to Lecture 3 of ES 300, Energy and the Environment. Today we're going to talk about net present value and project valuation. Last time, if you recall, we spoke about basic accounting and project finance. We talked about what a balance sheet was, how it might be indicative of um, a company or firm's ability to pay its bills on time. In other words, a measure of financial risk. We talked about what financing infrastructure meant, in other words, borrowing money to pay for it. We talked about the two main mechanisms for financing infrastructure through debt and equity. And we talked about the trade-offs between those two, where debt is a legal obligation to pay the money back, but there's lower interest rates associated with it. And we also talked about how financing costs can impact the cost of electricity for consumers, especially if a firm was judged by a credit rating agency to have higher financial risk, indicating a lower probability of paying back the money it borrowed on time. It would have a higher interest rate associated with the money it borrows, and that ultimately means a higher cost for the power plant and higher electricity prices for consumers. So all in all, what that lecture was meant to describe was sort of the general mechanisms for how utilities might get the money to build power plants. So today we're going to take a different track. We're going to assume that the utility was able to acquire the money to build the power plant. Now we're going to sort of put ourselves in the shoes of an electric utility and ask whether or not a particular plant is a good financial or economic decision. And we're going to talk about different metrics, or one metric in particular, net present value, for sort of deciding whether a particular investment, for example, a power plant, is a good decision. So here are the three questions for today that are sort of the quasi-final exam-like questions that you should sort of be asking yourself as you go through the lecture. The first is, what factors determine the long-term value of investments that are made today? Second question, how do we compare two different projects to determine which one is a better investment? And the third one is, how sensitive are our estimates about some of these questions to uncertainty in different areas? So let's start with a little thought exercise. Let's assume you didn't have to buy any books for this online class, so you probably have like $1,000 in your pocket extra. Just kidding. How much will that $1,000 be worth in 10 years? So let's assume that we don't do anything with the money. We just sort of stuff it in our mattress. In 10 years, we'll still have $1,000 in nominal currency. But of course, it won't actually be worth $1,000. It may be impacted by inflation. We're not going to actually talk about inflation today. Let's assume that we live in a world without inflation. There are other things that could influence how much that $1,000 is worth in 10 years. For example, what if we decide not to just stuff it in our mattress, but to invest it or save it in some way? So, for example, what if we save the $1,000 in a way that earns interest? So we've already sort of talked about in lecture 2 one particular way that we could earn interest on that $1,000. We could lend it. We could lend it to a bank. In other words, put it in a savings account. We didn't talk about that last time, but we did talk about lending it to a company or even a government by buying a bond. We could also invest it in a company. We could buy equity or shares in a company. So let's talk about bonds. First, this is going to be a bit of a refresher from last time. So we could buy bonds that are sold by the federal government. We could buy bonds that are sold by Duke Energy. And these are what we would call fixed income investments. All that means is that when we buy a bond, we're sort of guaranteed, for the most part, a nominal rate of return or interest rate on the principal of the bond. So the principal would be the amount of money that we're lending, or the face value of the bond. So let's say we buy a $1,000 bond. So that's the principal of the bond, and the interest rate attached to it is 4% per year. And we know that in advance. When we buy the bond, we know we're buying a bond. that earns 4% interest per year. And there are lots of different sort of payout structures for different types of bonds that you can buy. This is a really simple case where the coupon payment or the interest rate payments are made every year. So let's say in year 0, we are lending Duke Energy or the federal government $1,000. So that's the time that we're buying the bond for $1,000. And then in year 1, we earn 4% of the principal of that bond. So 4% of $1,000 is $40. We earn that same amount in year 2, in year 3, and all the way through year 10, which we're going to assume this is a 10-year bond. So that's when the bond matures. In year 10, we also earn 4% interest, so another $40, plus we get our principal back, so $1,000. So in year 10, we actually get $1,040 back. So if you add all of that up, 10 years worth of 4% annual interest rates, or interest payments on $1,000, plus our original principal, what we end up with at the end of 10 years is $1,400. So we started out with $1,000 and we ended up with $1,400. And this is a special case that I'll call your attention to, where the interest is not being reinvested. In other words, in year 1, when we earn $40, we are then stuffing that $40 in the mattress. We're not reinvesting it in another bond or some sort of other investment vehicle. So let's look at a different case here, which would be sort of a standard savings account mechanism where the interest does reinvest or compounds over time. So we start out with $1,000 in some sort of savings account in year 0, and that $1,000 earns 4% in the first year. So we earn $40. And so we're writing this a little bit differently because the interest is compounding and we're not receiving some sort of distinct coupon or interest rate payment from a bond that we bought. It's all, the money's all staying in one account. So in year 1, the way we express the total of money that we have after year 1 is to say we earn the amount of money that we have at the end of the year is 1.04 times the amount of money that we had in the beginning of the year. So 1.04 is, in other words, another way of saying all the money we have at the beginning of the year plus 4%. So all the money at the beginning of year 1 plus 4% is $1,040. So that's how much we have at the end of year 1. At the end of year 2, all the money that we have at the beginning of that year is not $1,000, it's $1,040, because that's how much we had at the end of year 1. So all the money that we have at the end of year 2 is $1,040 times 1.04. So 4% of $1,040 is $41.60. So if we add that $41.60 that we earn in year 2 to the beginning of the year total, which was $1,040, we end up with a grand total at the end of year 2 of $1,081.6. And so we can keep going in that respect. And so $1,081.60 becomes the beginning of the year funds in year 3, which we are earning 4% on that, and so forth and so on. And you can go from year 1 all the way down to year 10. And what we have at the end of year 10 is $1,480.24. And so I've also shown here in yellow another sort of way of writing the amount of money that we're going to have in year 10 in a straightforward way, so that we don't have to year by year add up all these numbers. So if we wanted to figure out how much money we were going to have at the end of year 10, given the fact that we start out with $1,000, we earn 4% per year, and we're going to leave the money in this account for 10 years, assuming that all the interest is compounding or reinvested, we can calculate that using this expression shown in yellow at the very bottom, which is $1,000 times 1 plus the interest rate to the 10th exponent, or to the 10th power. So just to give you a sense for how interest rates matter in compounding savings or investment vehicles. Let's assume that we started out with $1,000 in year zero. And there are three different choices for where we can put the money: a savings account that earns 2%, 4%, and 6%. And then we're going to leave it in the account over 10 years. And so at the bottom of this figure, it shows years 1 through 11 instead of 0 through 10, but it's the same thing. The main difference, the main point here is to show how the amount of money in the savings accounts diverge over time across those three different interest rates, right? So at the very beginning, they all start out with $1,000. And for the first couple of years, they're all pretty close because they're still all earning a relatively small amount of interest per year. But over time, the compounding effects of the interest rate starts to create a pretty significant divergence among these three lines. So you can see 4% is in the middle, and 6%, the green line, is on top, and 2%, the purple or red line, is on the bottom. And once we get to year 10, the vertical difference on the y-axis here between the the ending value of these three savings accounts is pretty substantial, on the order of a couple of $100s. Okay, so let's do another similar example, a slightly different question. Let's say we don't know how much money we have today per se, but we know how much money we want to end up with 10 years from now. So there are lots of questions that might be applicable to this type of thinking. Think about how much money your parents or you might want to have in order to be able to retire, and knowing at what age they want to retire, and roughly having an idea of how much money they need to do that, or saving for a kid's college, or saving up to buy a house or a car or anything else like that. So let's say we want to have $1,500 10 years from now. And we know that there is a savings account available to us that earns 3% compounding interest per year. Now the question is, how much money do we have to invest today in that savings account to have exactly $1,500 10 years from now? So we're going to think about it in a similar way to what we just looked at. This is the example we just saw where we had $1,000 earning 4% per year. And if you sort of understand how we got from year zero to year one, where we earn 4% principal on that $1,000, and at the end of the year we have $1,000.40 or $40, and that 1,040 serves as the beginning year money in year two, and we earn 4% on that, and that gives us 1,081 and 60, and so forth and so on. And remember, in year 10, the expression for the value of money that we have in year 10, we could write in this pretty succinct, elegant way, where we say the amount of money we start with is $1,000 times 1 plus the interest rate, which is 4%, all to the 10th power, to the 10th exponent. That is a way of getting at that same value that we have in year 10, $1,480.24. So if we take that more generic formula and say the principal is what we start with, we call what we start with the principal, and that was $1,000, and the interest rate was 4% or 0.04, and the time duration, or how long we're going to leave the money in the savings account, was 10 years, we can write that in an even more generic way, assuming that we don't know the specific value of the principal, the interest rate, and the time duration. And we can say that the money we have in year T is equal to P, or the principal, times 1 plus R, where R is the interest rate, and both of 1 plus R is within a set of parentheses, all to the T power, where T is the time duration, or how long we're going to leave the money in that savings account. So if we think back to the question we're asking, which is how much money do we need to invest today in order to get $1,500 in 15 years, this just turns into a pretty simple word problem where what we're trying to find is the variable P, or the principal, the amount of money that we need to invest today. We know the interest rate. We said at the very beginning that we know the interest rate associated with this savings account is 3%. And we know the time duration. The time duration is 15 years. That's how long we're planning on leaving this money in the savings account. So we can fill in the blanks here. We're going to say we're looking for year 15 money is equal to P times 1 plus 0.03. 0.03 is the interest rate. And we're going to be taking that to the power of 15. So in the exponent, we have t equals 15. And then we can fill in a little bit more information here. So year 15 is equal to P times 1.557. So where 1.557 is coming from, that's just 1.03 to the 15th power. So if you put that in a calculator or an Excel and you said 1.03 to the 15th power, you would get 1.557. So then we can fill in even a little bit more information because we know that the year 15 money, we want to be $1,500. That's how much money we want to have in 15 years. So now we have only one unknown, the letter P here. So we have $15 is equal to P times 1.557. And the way we get P, of course, is pretty easy. We can just divide both sides by 1.557. And that gives us with our final answer of P is equal to $962.79. In other words, if we want to have $1,500 15 years from now by investing in a savings account that earns 3% interest, how much do we have to put in that account today? The answer is $962.79. So we can sort of double check our answer here by working backwards. In other words, we can plug in the principal that we think we need into the equation and apply an interest rate of 3% and a time duration of 15 years and see if we get our desired outcome, which is $1,500. And so the way we would do that, we'd plug this into the same equation where now in this case, year 15 is our unknown. We know P, we think we know P, which is $962.79. And the value in the parentheses is 1 plus 0.03 or 3% interest. And the time duration is 15. And sure enough, we get our answer, $1,500. So this equation works. So let's add a little bit more terminology here. So we're going to refer to future value versus present value here. So the future value is the amount of money that we're going to have in the future. And the present value is the value or the money that we have today. So if we're thinking about future value, we're going to refer to that as the left-hand side of the equation here, which is the $1,500. And the present value, we're basically going to say is the principal, how much money we would potentially save in that savings account or put in that savings account today, right? So the yellow is the future value of $1,500 and the green is the present value, the principal. So we can come up with a even more sort of generalized abstract representation of this equation. At the very bottom here, we're going to say FV, which is in dollars, is equal to PV times 1 plus R in the parentheses, or R is the interest rate, to the T, where T is the duration. So this is a generic formula for relating what we would refer to as future value, so some amount of money that we're going to have in the future in present value terms, right? So there's some sort of relationship between future value and present value, and the way that they're related is by this other term on the right, 1 plus R to the T. So what this gives us an ability is to estimate future value as sort of a function of or given an initial amount of money or principal and some sort of assumed interest rate and time horizon. So let's do another example just to be sure that we're all sort of on the same page here. So let's look at that in terms of the more generalized equation that we just derived, or FV is equal to PV times 1 plus R to the T. So in this case, what's our future value? Well, our future value is what we want to have in the future. And so that's $1,200. Our present value is what we're looking for. That's what we're trying to figure out, the principal that we need today. How much money do we need to invest today in this savings account in order to have $1,200 in the future? What goes inside the parentheses is 1 plus R. R here is 5% or 0.05, so we have 1.05 on the inside of that parentheses. And T is our duration, or how long we're going to leave the money in the account, and that's 10 years, so T equals 10. So the second line here, we have $1,200 is equal to PV, that's our unknown that we're looking for, times 1.05, times 1 plus 0.05 to the T. So the first thing I like to do is to get rid of that exponent, so we can say that right-hand side of the equation is just equal to PV times 1.63. So where 1.63 comes from is 1 plus 0.05 to the 10th power. So if you plugged into your calculator 1.05 to the 10, you would get 1.63. So then our equation looks a lot less complicated. We have $1,200 is equal to PV times 1.63. We can solve for PV by dividing both sides by 1.63. And so if you put in your calculator $1,200 divided by 1.63, what you end up with is a present value of $737. So what that means, in other words, is that if we wanted to have $1,200 in a bank account 10 years from now, and that account earns 5% interest per year, today we would have to invest $737. So I hope everybody at this point is a little bit comfortable with this generic way of describing the relationship between future value and present value, assuming some sort of compounding interest, right? So future value is equal to the present value times 1 plus R to the T. So we can also flip this equation around, because so far we've just been describing future value in terms of present value and some other stuff. We can also describe present value as a function of future value and some other stuff. So the way we would do this, if we wanted to get the PV in dollars by itself, is we could divide each side by the stuff in the parentheses and the exponent, right? So we could divide both sides by 1 plus R to the T. And if we did that, we would get PV is equal to future value, FV, divided by 1 plus R to the T. And so there's something special about this second equation, which is it gives us an ability to sort of evaluate what the future value of some sort of amount of money is in today or present value terms. So it's, in a lot of ways, it's another way of writing the same word problem, right? How much money do we need today, or present value, in order to have a certain amount of money, the future value, or FV, at some point in the future? So this equation is also important for another reason as well. In particular, what it gives us a way to do is evaluate future revenues or costs of a project or investment, all in terms of a single present value. So PV equals FV divided by 1 plus R to the T. So if we're thinking about the relationship between present value and future value, and let's assume that R always has to be non-zero and positive, right? So let's assume the interest rate, or whatever rate our present value is accumulating in wealth until it reaches some sort of future value, has to be greater than 0, and it can't be negative. What does that mean? What can we always say about present value and future value? In particular, which one is higher? So if R is positive, that means that 1 plus R to the T is always positive and larger than 0. And so if we say PV is equal to FV divided by something that's greater than 0, What that means is that FV is always going to be larger than PV. So the formal way of expressing what I just said, which is that well, if we look at this equation, present value is equal to the future value divided by 1 plus r to the t, and that meaning that numerically the present value is always going to be smaller than the future value. This is what we call the time value of money. And what that means is that revenues, but also costs out into the future, matter less. We value them less than revenues and costs that we experience today. And this is an idea that has really, really important implications for a lot of different things, for how we value investments, including infrastructure like power plants, but also how we think about solving really difficult challenges like climate change. And we'll talk more about both in the rest of this lecture.